We're whizzing through these real quick. Algebra 1 already. We're going to be doing these linear equations, linear graphs, and getting into some more complex variables from the pre-algebra. So with Python, no problem. Let's go do this. Day 47 on the Space Lunar SS. I'm still trying to figure out Algebra 1 on Python mathematics. So in our pre-algebra video, we covered expressions, exponents, radicals, polynomials, linear equation. We did graphing. So in our Algebra 1, we can take a deeper dive. Let's jump right into piecewise functions. So piecewise functions are functions that are defined by different expressions or rules for different intervals of its domain. So these functions are useful for like modeling situations where the behavior of some graph or something changes abruptly at specific points. So in Python, you can create piecewise functions using the numpy, the NumPy module that we can import. So first thing we're going to do is import that module, numpy as np, and we're going to import matplot library dot plot as plt. And as you can see, these are not accessed, so we're gonna have to generate that virtual environment. I'm gonna go into my V environment folder and I'm gonna run this activate PowerShell by doing the ampersand. And now we're activated. You can see this green header here showing that we're in the V environment now. So now that I run this, we should be able to get no errors. So now that our packages are working in our virtual environment, we can define the sigma function, which is the first function that we're doing with this piecewise calculator. So we're going to return np piecewise x, and in our array we can build an array of x is less than 0, which is just a placeholder, and then x is greater than or equal to 0, and then 1 minus 1, and then a 1. So this is kind of the sigma algorithm that happens in that equation. And now we can make x value. So with the x we can do np linear space. So we're just putting in coordinates on like a graph with this one. And we could put in the y coordinates. With the y sigma, which passes in the coordinates of x. And we could plot the result. So we could do plot x, use that sigma function that we created up here, which grabs our x coordinate on the linear space. We'll create a marker and we'll have the marker as a O. We could add a line style. I'll just pass in a standard line, a dash. And then we could put in a label like a sigma function, which just kind of shows what it's doing. And then we could put in our labels like the X label. We could make the Y label. We can give it a title. We can activate the grid, add a legend, and make sure that it shows. So now if I run play, we can see our sigma has mapped out our linear spaces. Here's our coordinates, and here is the piecewise formula running the equation to then calculate out this graph. So that is a piecewise sigma function. And we can also do a transformation. So a transformation is something that modifies the shape, position, or orientation or functions of data. So common transformations include, shifting or reflecting or dilating different lines on a graph. So the way that we would do this in Python is, let's create the original linear function that we will then transform. So let's say we got this equation like f function x equals 2x plus 3. And we can define this linear function. And we could return a value. This is just the formula for the linear function. We're multiplying it by the x, and the x is going to be the same one that we've passed into this linear function. And now we will apply a translation, a shift, by adding 5. Transformation. So now we're going to be doing the transformation, right? So we'll make another function here, which is going to be the transformed function. So it's also going to be x, right? We're taking in this, and we're going to transform it by doing return linear function plus 5. And now we can generate the x value. So far, x doesn't have a value, right? So we're going to go ahead and assign value to x. So x values equals, here we're going to graph those coordinates on the graph, on the plot. So just these are like random coordinates that I'm picking. And now we're going to go ahead and evaluate. We're going to feed in the original and the transformed models. So we can do y original equals linear function x values. And we'll do y transformed equals transform function x values. And of course, in these x values, we are passing in this equation of the linear space onto the coordinates that we've passed in. So finally, we're just going to plot the results. So we're going to make sure that we can see it on the graph. So we'll do the matplot, x values, original, and we can add a label to it just so we can keep track of what's going on here. So we can see that this is going to be our original. And our next one is going to be our x values, y translated, transformed. And we'll add another line, a label on here, which is the transformed version. Of the same equation. we'll add the x label, and we'll add the y-axis label. Linear function and transformed version. And we'll do plot legend, plot show. So if I run this now we can see that we have an original line, right? The blue one. And then we have a orange transform line. And if I close this, we can run this again by adding, let's say, 10 to it instead of 5. And now if I rerun this, we can see there's a bigger gap in between the two now. So now let's move on to another topic in algebra called Quadratic Formulas. So quadratic formulas are stuff where we can look at stuff like so with quadratics, I'm just going to import the math function here, or the module I mean. And we can go ahead and define quadratic roots A, B, and C. And we can calculate the discriminant by doing D equals B to the power of 2 minus 4 times A times C. And these are going to be the values that we pass in our function. And D is going to be our constant variable. So if D is greater than 0, we can do two different roots. We got root 1, which is B plus math.square root on the constant divided by 2 times A. And then root 2 is also going to be negative B minus math square rooted by the constant divided by 2 times A. And then print roots are real and different. So I could print out a couple F strings for both of my roots. So we run this function block if D is greater than 0. But if D is just 0, then we're gonna do just one root. We'll do root equals minus B divided by 2 times A. And then we're gonna print out roots are real and equal. And if there's any other input for the D constant, so if it's not greater than 0 and if it's also not equal to 0, then we're gonna do this else for the default output, where it's gonna be real part equals minus B 2 times a. And we'll have an imaginary part since it's not the real part. And we'll do minus d on that constant. And we'll do roots are complex. And then put in one last f string here. And this one's going to be the subtract. Since root 1 was established, we're doing addition, and root 2, we're doing subtraction. So here in the end, we can print out that, you know, the real part, root 1, is an addition. Real part of root 2 is subtraction. And here we can activate this by doing A, B, C, you know, passing in this first array here because we still haven't assigned these numbers yet. And here I could put in whatever numbers I want. So let's do like 5, 43, and minus 15. And then I'll do quadratic roots, A, B, and C. Just pass these variables in here. Let's run this and see what we get. So I'll just add in a couple random numbers like 1, 10, minus 24, and I'll do quadratic roots and pass them in as the variables to pretty much execute my script. And we can see our output says roots are real and different with a 2 and a minus 12. And if we pass in some other numbers, like let's just say 0, 0, 0, we just get an error because this is kind of like an impossible equation. We got to put in some numbers here, like maybe 5, 10, minus 10. So here you go. And if you wanted to dive into complex roots, we can add in another import for CMath. And with CMath, we have a module we can import. Where we can define complex quadratics. We'll do D, E, and F as our variable names. And we'll calculate our discriminant again. So now I'll pass in a capital G as our constant. And our G is going to be E times 2 minus 4 times D times F. And now we're going to find the roots using CMath. So here we could do root 1 equals minus E. Subtract by CMath square root G. And divide this by 2 times A. And we're going to add another line of this for root 2, which we're going to flip this subtraction into addition. And here we can print out roots are complex. And we could print out our F statements to deploy these roots. So root 1 we'll do root 1 with this float, and we'll print out our second float with the string in it, root 2 . And we can go ahead and run this by doing D, E, F equals 1, 4, and 2 or something like that. And we'll do complex, quadratics, D, E, F. And now we'll pass those through here. How come I got a J in these? Roots are complex, and it's giving us the equation. Where is the J coming from? I'm not I'm not expecting a J. Alright, well, I'm getting a J in here. I don't know why exactly I'm getting the J. If you guys know why a J is coming in, what the bug is, let me know in the comments down below. Maybe it's something I'm not. So we're going to import the math module, and we're going to try to calculate e to the power of some number for to figure out what the value of x is. So that can be like for a specific value of x. You could do x equals 3.5, and we'll do result equals math.xp, assign it to x, and we could do print. We'll do an f string for e to the power of whatever x is, and we'll pass in our result. So we can see e to the power of 3.5 equals 33.1155. Another way to do this exact same thing is we can do result equals math.e to the power of x. So remember, when we put two multiplications together, that's like exponentiation. So now we can do x, and we can do x equals like 4. And we can print out another f string here to do e to the power of whatever our x value is. And we'll do result equals result 1 and if you run this, it's kind of giving out a similar response. So if I were to put in that same number, 3.5, then we could see this number down here, and the first way that we did it is the same number. So here's like the same way to do two different ways. Seeing. So next we'll be talking about descriptive statistics. So these summarize data and provide insights into kind of like averages and variables. So there's a couple different ways to do these statistics. So one way is we can import pandas as PD. And if you were able to have some kind of URL with a data set in it, you could do like URL. And as an example, here's a GitHub data set, something about like blood pressure records from like some doctor or something. So here we could do df at pandas read CSV URL, and we could use this to display info about the data set. You know, this one up here, this loads the data set. So if I run play here, alright, so we just don't have the module pandas. And that's fine, we can get into that later, but the main thing I'm trying to get into is we have another way where we can just create our own data set. So I'm going to import numpy again as np, and from statistics I will import module, and I'm going to create a data set here, and it's May right now, so we'll do like May temperatures. So, you know, May the 1st it was 60 degrees Fahrenheit. May the 2nd it was 65 degrees Fahrenheit. May the 3rd, let's say it was like 69 degrees Fahrenheit. Let's say the next day it just went down to like 14. It didn't actually, but let's just say it did. Next day, next day was like 105. Oh my god. Crazy weather out here, so I'm just feeding in a bunch of numbers. So here's a data set of different days throughout the week and the temperatures that it's getting to. And now we can do a couple things with this. We can calculate the mean. So the mean of May temps equals np.mean and the May temperatures. We can calculate the median. So mean May temps equals np.median we can calculate the mode the same way. So we'll do, oh my bad. Mode of May temps as, so it's just as easy as this, like you don't even really need to know, because we could just get NP to do all the work for us. And we can calculate variance. Doing variance. np.var the May temps, and we can also calculate standard deviation. We'll do np.std May temps, and here we can just kind of display results. And I'll just print these all out with f strings. So our first f string is going to be talking about the mean. So we'll do mean May temps, and we'll put out the small float. It's not going to be a big number. And then medial is kind of just like, median is kind of just the middle value. Next we'll pass in the mode, which is the most frequent. And next we'll pass in the variance of age. Next we'll pass in the variance of the temperature. So mode, nope. Yeah, variance. And pass in the float. And lastly, we'll pass in the standard deviation. And we'll do the standard. So if we run this, alright, so this is not accessed, so I can just delete this. I'll just import statistics as whole. Okay, it looks like mode isn't something I can pass in. Is it just mod? Alright, I see what I was doing wrong. So I had module up here. This is supposed to be mode. And I scroll down, and this is not NP mode. This is just mode from the statistics. So now if I run it, now we can run all of our little equations. So we can see the average temperature was 57 degrees, the median was 62, the most frequent was 60, and the variance of the temperature is 849, whatever that means, and the standard deviation is 29 degrees. So that's all. We wrapped up this video, and I'll see you guys on geometry on the next video.